In this episode, we start with several cryptography-related ideas that can look similar from a distance but solve very different problems. Hashing, salting, digital signatures, obfuscation, and crypto tools all deal with protecting information or supporting trust, but they do not all provide encryption. That distinction matters because a lot of confusion comes from treating every security technique as if it hides data in the same way. Hashing helps you check integrity. Salting helps protect stored passwords from certain attacks. Digital signatures help prove identity, integrity, and non-repudiation. Obfuscation makes something harder to understand, but it is not the same as true encryption. Crypto tools and utilities help people generate keys, inspect certificates, calculate hashes, sign data, verify signatures, or encrypt information, depending on the purpose. The goal is to help you hear a scenario and recognize what kind of protection is actually being described. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.News in the Bare Metal Study Guide series. Hashing is a process that takes input data and produces a fixed-length output called a hash value, message digest, or digest. The input could be a file, a password, a message, a software download, or almost any block of data. A good hashing process is designed so that even a small change in the input creates a very different output. This makes hashing useful for integrity checks. If you download a file and calculate its hash, you can compare that result to a trusted hash value from the source. If the values match, you have evidence that the file did not change between the trusted source and your copy. If the values do not match, something is wrong. The file may be corrupted, incomplete, altered, or not the file you thought you received. Hashing gives you a way to notice change. Hashing is not encryption because it is not meant to be reversed. With encryption, the idea is that someone with the correct key can decrypt the protected data and recover the original information. With hashing, the normal design goal is different. You calculate a digest from the input, but you should not be able to take the digest and rebuild the original input. This one-way nature is why hashing is useful for comparisons. A system can compare hash values without needing to store or reveal the original data in the same way. But you should not overstate what hashing does. A hash does not keep a file secret. Anyone who has the file can read it unless some other control protects it. Hashing helps show whether data changed. It does not automatically make data confidential. Hashing can help with software integrity, evidence handling, file validation, and security monitoring. If a trusted software publisher provides a hash for a download, you can compare the hash of your downloaded copy to confirm that the file matches the expected version. In an investigation, a hash can help show that a file collected as evidence has not changed during handling. In security monitoring, hashes can help identify known malicious files or confirm whether important system files have been altered. You should think of hashing as a fingerprint for data, with one caution. It is not a perfect human fingerprint comparison, and weak hashing algorithms can create problems. The value comes from using a strong hash function and comparing the result against a trustworthy reference. If the reference value is not trusted, the comparison is much less useful. A hash collision happens when two different inputs produce the same hash value. In a strong hash function, collisions should be extremely difficult to find in a useful way. In a weak or outdated hash function, attackers may be able to create collisions or take advantage of known weaknesses. That matters because hashing is often used to support trust. If an attacker can create a different file that produces the same hash as a trusted file, integrity checking becomes weaker. This is why older algorithms eventually fall out of favor. You do not need to memorize every algorithm weakness at this stage, but you should understand the pattern. Cryptographic methods age. What was acceptable years ago may no longer be safe. When a scenario mentions outdated hashing, weak algorithms, or collisions, the concern is usually that integrity checks or trust decisions may no longer be reliable. Salting is closely related to password storage. A salt is a random or unique value added to a password before the password is hashed. The purpose is to make password attacks harder, especially attacks that use precomputed hash tables or compare many users at once. If two people choose the same password and there is no salt, their password hashes may be the same. That gives an attacker useful clues. With proper salting, the same password can produce different stored hash values because each password is combined with a different salt before hashing. The salt does not need to be secret in the same way a password does. Its job is to make each password hash more unique and to reduce the value of precomputed attacks. The password still needs to be strong, and the hashing approach still needs to be designed for password protection. Password hashing deserves extra care because ordinary fast hashing is not always enough. General hashing is often designed to be efficient, which is useful for checking file integrity. Password storage has a different challenge. If attackers steal a password database, they may try many guesses very quickly. A password hashing approach should slow down guessing and make large-scale attacks more expensive. Salting helps, but it is not the only protection. Strong password storage may also use methods designed to be computationally demanding so attackers cannot test guesses as quickly. You do not need to configure those methods here, but you should understand why the goal is different. For a file integrity check, speed can be helpful. For password guessing resistance, too much speed can help the attacker. The same word hashing appears in both places, but the security need is not identical. Digital signatures use cryptography to support trust in a different way. A digital signature can help prove that data was signed by the holder of a private key and that the data has not changed since it was signed. This supports integrity because changes should cause signature verification to fail. It supports authentication because the signature can be connected to an identity through certificates and trust relationships. It can also support non-repudiation because the signer may have a harder time denying the action if the private key was properly protected and the signature process is trustworthy. A digital signature is not just someone typing a name. It is a cryptographic result that can be checked later. When you see signing in a scenario, think about proof, trust, and change detection rather than secrecy alone. Software signing is a common use of digital signatures. When software is signed, the signature helps show that it came from the expected publisher and was not changed after signing. This matters because attackers may try to distribute altered software, fake updates, or malicious code that pretends to be legitimate. A valid signature does not mean the software is perfect or that it has no vulnerabilities. It means the system has evidence about the publisher identity and whether the signed content changed after signing. If the signing key is stolen, the situation becomes serious because attackers may be able to sign malicious software in a way that looks trusted. This connects back to private key protection. The value of a digital signature depends heavily on the signer's private key being controlled and protected. Digital signatures and hashing often work together. The signature process does not usually sign an entire large file directly in the way a person might imagine. A hash of the data can be created first, and then the signature is applied in a way that protects that digest. Later, the verifier can calculate the hash again and check whether the signature and current data still match. You do not need to follow every mathematical step to understand the meaning. The signature gives you a way to verify that the content is still the same and that the private key holder was connected to the signing action. This is why digital signatures support integrity and trust. Encryption focuses on keeping information secret. Digital signatures focus on proving origin and detecting change. The two can be used together, but they are not the same job. Obfuscation is different from hashing, salting, encryption, and signing. Obfuscation means making something harder to read, understand, or analyze. A programmer might obfuscate code so it is harder for someone to reverse engineer. A script might be written in a confusing way to hide what it is doing. Malware authors often use obfuscation to make detection and analysis harder. Some organizations may also obfuscate certain data or code to reduce casual exposure. But obfuscation is not the same as true encryption because it does not necessarily rely on strong cryptographic protection and a properly managed key. It may slow someone down, but it should not be treated as strong protection for sensitive information. If a scenario asks whether obfuscation protects confidentiality like encryption, the safe answer is no. It hides or disguises, but it does not provide the same assurance. That distinction matters because obfuscation can create a false sense of security. If sensitive data is only disguised, encoded, renamed, rearranged, or hidden in a confusing format, someone with enough time or skill may still recover it. Encoding is another idea that is often confused with encryption. Encoding changes data into another format for handling or transmission, not for secrecy. Obfuscation changes appearance to make understanding harder, not necessarily to provide strong protection. Encryption protects confidentiality through cryptographic methods and keys. Hashing supports integrity and comparison. Signing supports trust and change detection. These differences are important because choosing the wrong technique can leave data exposed. If you need confidentiality, use encryption. If you need to detect change, use hashing or signatures. If you only make something messy to read, do not pretend it is secure. Crypto tools and utilities are the practical ways people work with these ideas, but you should think of them by purpose rather than by product name. Some utilities calculate file hashes so you can compare a download against an expected value. Some tools generate key pairs or certificate requests. Some inspect certificates so you can see the subject, issuer, expiration date, and trust chain. Some sign data or verify signatures. Some encrypt files or storage locations. Some manage keys in a controlled service. The tool itself is not the security goal. The goal is what the tool helps you do. If you use a hash utility, you are checking integrity. If you use a certificate viewer, you are inspecting trust information. If you use a signing utility, you are supporting proof of origin and integrity. Always connect the tool to the security purpose. You should also remember that crypto tools can be misused. A strong encryption utility can still produce weak protection if the password is poor or the key is mishandled. A certificate request process can still be risky if the private key is generated on an untrusted system or copied too widely. A hash comparison can still be meaningless if the expected hash came from the same untrusted place as the file. A signing process can still fail as a trust control if the signing key is exposed or shared too broadly. Tools do not remove the need for judgment. They help apply cryptographic functions, but people and processes still determine whether keys are protected, algorithms are appropriate, trust anchors are valid, and results are interpreted correctly. In security, using a tool is never the same as understanding the control. For exam scenarios, listen for the problem being solved. If the issue is whether data changed, hashing may be the answer. If the issue is stored password protection, salting and password hashing may be involved. If the issue is proving that software came from a trusted publisher and was not altered, digital signatures may be involved. If the issue is making code harder to understand without providing real confidentiality, obfuscation may be involved. If the issue is keeping data secret, encryption is the better concept. If the issue mentions a utility, ask what it is being used to do. Is it creating a digest, generating a key, requesting a certificate, signing data, verifying a signature, or encrypting content? The wording may vary, but the purpose will guide you. The conclusion is that hashing, salting, digital signatures, obfuscation, and crypto tools each have a specific role. Hashing creates a digest that helps you detect change and support integrity checks. Salting strengthens password storage by making password hashes more unique and harder to attack at scale. Digital signatures help prove origin, support integrity, and strengthen non-repudiation when private keys are protected properly. Obfuscation makes something harder to understand, but it should not be mistaken for true encryption. Crypto tools and utilities help people apply these ideas, but they are only as useful as the decisions behind them. As you continue studying, keep the purposes separate in your mind. Integrity is not the same as confidentiality. Disguising is not the same as encrypting. Signing is not the same as hiding. Clear distinctions will help you choose the right answer when the exam describes a security problem.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.